Good afternoon, everyone. Welcome back from the lunch. This afternoon, we go into a session of industrial perception and autonomy. I'm Eduard Krubasik. I'm chairman of the Industrial Council of Munich Institute of Robotic and Machine Intelligence. In my earlier life, I was on the Siemens executive board in charge of the automation businesses, saying it most generally. And today, we have a great series of speakers. We'll start with Dr. Gunther Kögel. He's the CEO of Pepperl & Fuchs, and he'll talk about the importance of sensors and cognitive capabilities. Then we'll hear Dr. Alfred Rizzi, chief scientist at Boston Dynamics, talking about deploying capable legged mobile manipulating robots. And after that, we'll hear Professor Matthew Mason, chief scientist at Berkshire Grey. Robotics and warehouse automation is his topic. And finally, Dr. Christoph Palo, project leader at the Digital Trust project in Robert Bosch, will talk about trustworthy AI and digital trust. What is digital trust? Starting with the presentation on the importance of sensors and cognitive capabilities for the next generation robotic AI systems, we have Gunther, who is an electrical engineer with a doctorate at the University of Darmstadt. He is the chairman of the executive board of Pepperl & Fuchs, one of the very famous sensor companies in Germany. He is also a member of the supervisory board of the VDE, and he has been president of ZVI, which is Germany's Electro and Digital Industry Association. And in this function, he has been one of my successors. So we both have come through the same line. Now, he will be talking about the lack of cognitive capabilities and the performance of industrial sensors as a bottleneck for robotic applications and even outside industry. So we'll hear a lot about the state of the art and trends and visions and requirements for the next generation of sensors. I'm looking forward to this. Very welcome, Gunther, please.
Yeah, thank you for the nice introduction. Ladies and gentlemen, it's now my duty after lunch to prevent you from falling into your well-deserved midday nap. I hope I can do so. It was interesting to see the other presentations because we are not only a sensor manufacturer, but at the same time also a large electronic manufacturer. And indeed, AI works nicely when we do recognitions of our boards in regards of completion of the complete surface mount process over there. But it only serves 5% of the job, because the major problem is not that we place all the components at the right place and the right orientation and the right, let's say, quantity. We need to look at the quality of the soldering joints. This is really the bottleneck over there. And in all honesty, we don't have a sensor that can do the job. There's X-ray, which is extremely expensive. You know that X-ray costs are actually not linear. So a one-dimensional X-ray is about $100,000. 2D is already $1 million, and 3D is $10 million. Yeah? So you don't have a 10 million machine for a simple X-ray process of manufacturing line in electronics. So we solved the problem by actually taking the boards, putting them in the fridge, cycling it 5 times. That makes all the weak soldering joints crack, and then we do an electronic test afterwards, simply because there is no sensors that can look virtually at a soldering joint and come up with an idea what the quality looks like. It's impossible to see this from the outside, and even with X-ray, you only detect 95% of the problems over there. Lack of sensors. I heard today that we shouldn't worry about sensors because with the 6G technology, sensors will come in for free. Terahertz technology will solve every problem over there, and this is relatively quickly. We are talking about 5G, 6G is just one generation, so let's wait a few years and all the sensor manufacturers in Germany and around the globe will run out of business because these chips will do the job over there. I believe he's true. I only don't believe in the time frame he's giving. And let me tell you a story that started more than 30 years ago. When I was a young scientist, we had at my alma mater in Darmstadt a science conference, and the young scientists were presenting their first ideas about AI. At that time, neural networks were still called amorph memories and stuff like this. So really the old days, and it was actually before AI doomed for quite 2 decades before we had the computational power to restart everything from the scratch. Even there, we already postulated, well, it should be able for us to beat a master in Czech in 10 years, so by the year 2000, and a master in table tennis, or let's call it ping pong. Yeah. There was self-confidence of young scientists over there, and guess what? We managed the Czech challenge pretty simply because of Moore's law. We had every 18 months duplication of computational power, and so the old algorithms of brute force actually did the job. We didn't do anything, no new algorithm, no nothing, just the old stuff with higher computational power, the thing was done. And what about table tennis? We have motorless drives, even robots that can actually move their kinematics in a way that they can hit a ball as precisely as a good table tennis player. Unfortunately, we don't see the ball. We have absolutely no chance to predict the curveball. Unfortunately, the ball is white. It doesn't have any markings, so you can't see the momentum, the drill, the spin. Nothing is visible for you. So we can't. Why do we lag so drastically behind? Why can't we simply see the ball like humans do? The simple answer is humans can't do it either. It is not possible for a human eye to actually track the speed in table tennis with his eyes. So how do humans do it? Actually, they do it with their brain capability in recognition by interpreting the actual movement of their opponent's body. So Timo Boll, as one of the world's best table tennis players, trained it several million times, and he automatically knows already where the ball will end. When he actually sees the movement of his opponent, he doesn't look at the ball. He doesn't have to look at the ball. This is unequal by any kind of machine, AI, or whatsoever that we can do this. Interpreting gestures is extremely difficult, and humans can do this into really artistic matters. When you see a table tennis player like Timo Boll playing, it's absolutely amazing how he can do this. And when he basically gives the ball a certain curve, a certain momentum or spin, the robots will not be able to hit the ball at all. So it actually looks pretty poor when you see a robot playing table tennis. 30 years afterwards, it's still not solved the problem, and still the bottleneck are sensors. And we still run into a trap that all of you have encountered multiple times. We think if robots can do things human can't, then automatically robots must be doing things easily that humans can do. And that's wrong. I mean, we can place miniature components in a tremendous speed of several hundreds per minute in an accuracy of nanometers, but a robot can't tie the laces of your shoe. Until today, he's not able to do it. Handling this kind of non-rigid material is still awkward for any kind of robots. And sensor manufacturers like we missed it. 30 years we were developing the next generation of sensors, but whatever we did was just to actually do the next specification, the next specific sensor that suited one particular very narrowly defined application. This we can do very well. So we have something like 50,000 different sensors that all fulfill a very specific tiny little task. We are far away from anything that you could call universal, because nobody wants universal sensors, maybe besides Huawei that wants to build the universal robot over there. But for industry, there is no need for universal robots or universal sensors. There's only a need for something that does it specifically and particular. And we're good in optimizing it, and we can actually beat humans as soon as we do a more and more narrow kind of specification. As soon as we specifically say we want to do exactly this and this and this, then it's easy to beat a human. As soon as we don't do this, as it's a general task and it's not well defined, then universal sensors are not existing. So when you look at our portfolio, for example, the upper two ones are our legacy products. What we do at the very moment is transforming them from analog into digital. So we heard from Google, yeah, we are taking all the data coming from the shop floor. Unfortunately, I have to tell you, there is no data on the shop floor. And let's take the chemical industry. In the chemical industry, the sensors like pressure, flow, analytics, temperature, level, they're all connected to the DCS system, and 95% of these connections, as of today, are analog, 4 to 20 milliamp signaling. There is no data. These sensors are integrated in simple control loops. So what they give is a measurement value that is irrelevant a nanosecond later. It's just something that feeds a control loop. It's not data. Anything that makes it data is still missing. We don't have the content information, so we actually don't know what it is. We get a pure number, and our a priori engineering of the entire design, control loop, and even machine tells us what this number represents. But upwards in the ladder, nobody can use this data because they lack all these additional information over there. That's the reason why everybody's so frantic about the digital twin, because the digital twin has all the relevant additional content information that makes this measurement value a data. But at the very moment, it's not data. It's just measurement values that you can get out of machines or out of bigger plants in the industry. That's the reality, and therefore the SAP people are always very disappointed if they ask us, well, you have sensors, please give us your data. And we said, yeah, we have sensors, but they don't generate data, not yet. We are about to do so, but first of all, we have to get rid of the analog connection of sensors to the machines. Now, guess what? Simply wiring an Ethernet cable into chemical industry is not allowed because it's an explosion hazardous infrastructure, and you're not allowed to wire standard cabling. So we first of all have to come up with an Ethernet wiring that is intrinsically safe. So it does not create any kind of arcing or sparking and makes the damn thing blow up over there. So these are trivial things we have to fight with at the very moment before we actually can do the next step of digitalization of our shop floors. This will take us another 5 to 10 years. Then we have the shop floor in a digital manner, and then we can start applying our data-based business models on top of this. So the industry is lagging behind quite substantially. That's the reason why we are talking about Industry 4.0 since 10 years, and we only have lighthouse projects. Whenever we go into scaling, it doesn't work, simply because the rest of the industry, the rest of the plant is not yet fully digitalized on the shop floor. We are working on this. We have funded an industrial twin association together with the VDMA, the Z4E and the VDMA, and we are having a fast progress in using existing standards and norms to actually do standardized of digital twins, because a proprietary digital twin doesn't help nobody. You need to fulfill data sets which are specified from different application viewpoints, and the more you have, the more easy it is to put simple applications on top of this. So we are not having a lag in regards of AI algorithms. There's plenty of it, and we can use them, but we don't have the natural data, and it's coming from sensors which are simply too poor to generate the necessary data that actually require artificial intelligence. So we need to go on to do this, but unfortunately, our own market, the industrial market, is much too small. If you would ask us, well, why don't you build a terahertz sensing platform like we just learned from URY? Because it basically absorbs several $100 billion, and the entire industry isn't able to finance this. So we need the impact, we need the technology transfer from other sectors which are much more quantity intense, such as gaming, very important for us. There wouldn't be a simple memory device just for the industry purpose. Memory chips were going down in price when we all started with the first gaming computers like VC20 or VC64 in the early 90s over there. Yeah? That was the starting stone for developing cheap memory capacity chips over there. Same as automotive. Automotive also, each car today already includes 960 chips, so they are actually going forward. When they talk about autonomous driving, they need a dramatically improved sensing capabilities. We learned it this morning. Driving in a circle in Indianapolis, that's nothing but autonomous driving. I mean, do this. You don't have to go to Neapolis to find the necessary traffic conditions. The inner city of Munich is already enough. With the many construction sites that they have, I can guarantee autonomous cars of today wouldn't run a single meter. They would immediately stop because they can't interpret what is around them. You need a priority knowledge about this to do this. And even as an experienced driver, you sometimes get lost in the many construction sites and traffic signs. Yesterday, the bus driver wasn't able actually to bring us to the right point because all of a sudden, the road was blocked by some pillars he didn't actually expect. So we had to walk the rest of the 200 meters to the venue in the residence. So we need this in the industry, but we need it from other sectors because our quantities are simply too small to justify these massive investments over there. And what will it be? Now, LiDAR technology, for example, is something that we developed to a certain degree just for an industrial purpose, and it took us over 20 years to come up with LiDAR that really use time-of-flight technology in a way that is applicable for industrial purposes. Nobody buys this at a price of 20,000 euros. It has to be down at 2,000 or maybe 1,500 euros. This is an accident, actually. The approach was that the inner city of Karlsruhe had some traffic accidents with the trams in the recent years because the racks were blocked, the tracks actually, and that made the tram go out of the tracks and hurt people. And therefore, they wanted to have a sensor that could look at the tracks actually before the train would be there as a kind of a perception of the last meter. So we installed it, but not in this way, but perpendicular to this, so that it actually could see the tracks. Accidentally, it scanned the entire city of Karlsruhe by moving through it. And what you see over there is not a photo, it's a printout of a 3D pixel cloud. What you say, every leaf of a tree is represented by an XYZ coordinate. But even this nice sensor picture already shows the many shortcomings of such a sensor. Too many spots that don't have any information at all because either it's blocked by objects. You see the black one. This is obviously an object like a bus or something like this running in front. So it is a 3D information. It's much better than a simple photo that has difficulties in interpretation, but it's by far not sufficient to really develop a complete recognition capability. But this is already something where you can apply a lot of specifically machine learning, deep learning algorithms to actually do something out of these pixel cloud data. So that's much more in the direction of what we heard from UOI this morning. Simple sensors generating massive pixel cloud information, and then AI algorithms doing the jobs to interpret it and to understand, okay, what's really behind it. So this kind of technology is a candidate for a more general or more universal sensor over there. What we in industry do, we take this technology and again slim it down and reduce it to serving just one application. For example, these transportation robots, they always have a problem if there's a forklift and you basically have a supervision of the floor. You can't see the forklift if the fork is up by only 10 centimeters. Then you simply ran into the forklift as you think the floor is clean, but it's not because the forklift's fork is elevated by some centimeters only. So we use this sensor to just have 4 lines, and that's enough to actually check out whether there's a forklift and to identify a pallet and stuff like this. So this is not a universal sensor anymore. It has the same time-of-flight LiDAR technology, but it's reduced into an application-specific requirement or application specification, by this reducing the universal behavior of the sensor, but this also means it can't be used for anything else but just this particular information. So we can do other things like guiding structures because we are in an industrial environment, and don't forget, industrial environment is highly artificial. It's not like an environment for human where everything is designed for human with their enormous capability of perception, recognition, and our priority knowledge. our industrial world is much more simpler and can be handled with much simpler sensors over there. Like, for example, this is a system where you actually have these QR codes stick to the ground, and the sensor makes sure your AGV, for example, has correct positioning. The nice invention here is that it's a fail-safe positioning, because we use multiple colors in the QR code and blend in and out the colors and have a redundancy on this way. So we make sure that we are not misreading these QR codes and having a safety integrity level 3 as a functional safety. So you can use it, for example, for positioning AGVs even when you have human traffic around. We continue to work on triangulation, several cameras. I know that Tesla actually thinks they can run cars automatically without 3D imaging, but just with several camera images. They basically do some triangulation measurement or calculation with it and generate artificial 3D images out of this. This works without any doubt, even in industrial applications. It's a typical grip-in-the-box application, but it is an interpretation still, and it runs into misinterpretations. We all know this from optical illusions. How often are we actually tricked out by optical illusions with our stereo cameras? By the way, our stereo camera has only a base wide of 10 centimeters, so in a distance of 10 meters, this isn't helpful at all. But still, I'm able to know that this tree is far away than the other. How do I do this? I can do this even with one side, blinded, because I know how to interpret light, shadows, and these things. That is a priori recognition capability that I have that robots lack. And maybe we can learn this with AI. Maybe we can learn this with deep learning. We are going into the direction of higher resolutions with these voxels arrays. So these are the active illuminating. And then we have chipsets behind that look like these 3D imagers. They are extremely poor at the very moment, very, very sensitive against ambient light. So whenever there's sunlight coming into the plant, forget your imager, it doesn't work any longer. So we still have to work some more generations to have 3D imagers. We hope that the information and communication people will do so and integrate them into the next iPhone, that your iPhone doesn't take simple pictures, but 3D holographic pictures. If that's an application, quantities will run into infinite numbers. This could be a technology we can apply nicely in the industry to really obtain more universal sensors. And then we could basically have an entire manufacturing surrounding in a 3D image. That's already a 3D image, but it's not real time. It takes something like 20 seconds to get an image of this. And this is only for demonstration purposes. But actually, we are currently using this kind of technology in the major assembly of aircrafts, because this is today a completely manual process that takes several days to have the right alignment of the different body parts over there. And you can automate this if you only have a 3D pixel-related information of the entire machine. But as you can see from this simple test bench, when it's difficult for humans to interpret what is that, then you can do the best sensing capabilities of the world. You still have to do the necessary learning. What is it? What shall I do with it? What's the right strategy to apply my task over there? You can see the different images. We even combine the time of flight 3D measurement with photoelectric color information. We call this Pixel Plus, because that makes it easy for humans to follow what the machine is doing, because we are very much linked to these colors. Machines are not, and therefore we at least have a nice way to actually show this at any kind of human-machine interface in a nice way. But interpreting such a scene and then understanding what do I need to do over there is something highly complex and yet not solved. And that's where AI actually kicks in. So let me summarize. Sensor technology development is still the bottleneck and prevents a faster progress in advanced robotics more than any other technology. It's not that we need quantum computers or whatever blockchain technology. First of all, we need better sensors if we want to proceed. We need to put effort in developing the next generation sensors. And yes, terahertz sensors will be something like this, but we are not talking about 2 to 3, but 20 to 30 years before we have this technology. I can tell you because I went through these last 30 years, and we had the same assumption 30 years ago. We will do all these jobs in 5 to 10 years, and even 30 years. We haven't been able to do this. And science, especially automation science, is not like a ketchup bottle. where you basically put and somehow plunge into there. It is a continuous process of improvement over there, and therefore I don't think that we should have high hopes that all of a sudden there is the universal sensor and there is a universal interpretation. It's hard work on science, and it's hard work in industry to do so, but I think there is a continuous process of improvement, a continuous process of having better sensors, but it's not so fast like we all thought 30 years ago, and like we maybe even today still think. Thank you.
Thank you very much, Gunther, for this exciting show that indeed there's a long way of working. It's much easier to have a far-out vision of the future than getting there.
Yeah.
Now, there are certainly some questions here. One, please.
Yeah, I agree that it's a very interesting talk, although there were a few statements that confused me a little bit. In the very beginning, you mentioned that the advancement in AI is mostly due to compute power. There are actually studies that say something different, so I just...
That's a misunderstanding. I always was concerning on the check play, that this problem was solved simply by increasing computational power. At the very beginning, we used the same brute force algorithms that we developed 20 years ago and were able simply because of computational power. I totally agree that there is a tremendous improvement in AI. What we did 30 years ago was a neural network of one layer, because computational power didn't allow us anything else. There was not even a theoretical model of multi-layers or maybe even coupled networks over there, which have all been developing. Although that's absolutely clear. AI did a tremendous progress in the recent years, but the check problem was not solved by better AI algorithms. That was solved simply by computational power. Which is different with Go. When you look at the Go play, that was only possible because of severe, better AI algorithms.
We may have time for one more question. There is one. Go ahead.
You mentioned that, maybe stand up, that gaming, for example, pushed the development of memory. The current sensors are actually not developed for robots. Usually you have sensors which were developed for TV, there were sensors which are developed for something else, which are used in robotics. So it's not only the sensing technology, but also the interfaces to the sensor. Do you see we should have something which is basically pushing interface development to the sensors? Because if the industry, everyone is doing it by himself, it will take another 40 years to get the sensor to control the robot. There is a completely different story between seeing something and controlling based on what you see.
Yeah, I think we have to precise on what we mean by interface. The interface from the device to the control station, that discussion is done. That will be Ethernet protocols in the one or the other way on the one or the other physical layer. Or it will be wireless 5G, 6G technologies. But the interface from the sensor device, the chip as such, into the application, this is something which is absolutely free, where we don't have any standardization. And in the VDE, where I'm the co-chairman, we have the DKE, which is the German Standardization Association, which brings forward all the nice standardization projects into XENELEC, which is the electrotechnical European standardization body. And we currently run massive campaigns to enhance and enforce this standardization work to address exactly these matters, that we can't have too many interfaces from a chip to the application internally in the device, simply because we haven't standardized this yet. So I absolutely agree, we need to do much more in standardizing. The digital twin is also a good example. Proprietary digital twins are not helpful at all. You need to have a set of standards, and that's hard work, and it's not fun. That's the worst thing ever than send someone into a standardization committee. It's boring, and it's a lot of traveling, and it's sometimes even without any success, but we have to do it. We have to do this.
Thank you very much, Gunther Kegel. Now, maybe we have a chance to hear a bit about sensors again when it's integrated in mobile platforms. Dr. Alfred Rizzi from the world-famous Boston Dynamics, his chief scientist there, will talk about it, namely about locomotion capability that rivals humans and animals. and control system that effectively use a robot to reliably interact with its environment, to pick, place, grasp, manipulate, and so on. He's chief scientist at Boston Dynamics, focusing on novel locomotion and mobile manipulation systems. He was also leading the Robotics Institute at Carnegie Mellon University. And he has a bachelor from Massachusetts and a master and PhD from Yale University. So welcome. Alfred, we are very curious. Of course, we have seen all your videos, and we are wondering what you're doing now.
Well, I'll probably show a few more videos today. I'll just make one correction, because the director of the Robotics Institute, when I was there, is the speaker after me. So that wasn't me. Thank you very much, though. Thank you for the introduction. Thank you, everybody, for coming today. It's a pleasure to be here. I think this is a really exciting gathering and an interesting set of discussions. I'll give you my secret. 30 years ago, when I was in graduate school, I also wanted to build a robot that could play ping pong. At the time, there was one machine in the world that played a very limited game of ping pong, and you weren't allowed to give it any spin, and I always thought that was wrong. Here we are, and I don't have a ping pong playing robot yet, but we do have robots that can walk, and maybe robots that can touch the world, which I think is exciting. What are we trying to do at Boston Dynamics? If you tracked our history, right, we've done a lot of work on locomotion, and we like to say that locomotion just works at this point. You can sort of treat a legged robot like a remote control car, tell it where to go, and the robot takes care of the details of figuring out exactly how to do that. I'll talk a little bit about how we made that happen, but the thing that we're really interested in at this point is moving beyond just locomotion and letting the robots reach out and touch the world around them and interact in a similar way. Again, would like to make it so that the operator, whether it's a human or some higher level reasoning system, can have a simple interface that's an effective way to tell the machine what it wants to do. That, of course, relates to the sensors on the robot and essentially what is the robot's understanding of that environment that it's interacting in. And I'll show you some examples of how we've been doing that. The strategy that we're using to do this is we're not trying to solve all the problem in one fell swoop. We're trying very systematically to build up from a set of low-level capabilities. So we build in these basic behaviors in the robot, and then we use people to play the role of those higher-level systems and control and operate them. Look at how the people use those systems, look at how effective they are at executing tasks, and use that to refine our designs and hopefully ultimately deliver capabilities that are packaged up in a way that an autonomous system could actually be effective at walking through and manipulating the world. Almost, there we go. A little bit of history. This is sort of projects I've worked on at Boston Dynamics in 4 simultaneous video forms. The first thing on the top left is a robot called Little Dog. This is actually a project I worked on like literally day one when I started at Boston Dynamics in 2006. And we had to develop the hardware around this robot and deliver it out to a bunch of university groups who used it to do research on machine learning related to locomotion. The sensing problem was completely taken out of this particular project. The teams had prior maps of the environment they were going to locomote across, and there was an external sensing system, a motion capture system, that kept track of where the robot was relative to that terrain. So there was no sensing. The second thing is a robot we call Flea. It's a little differential drive robot, except it can hop, and it can hop 10 meters. And it can actually do that 30 times. The trick is, and nobody gets it, everybody thinks we wind up a spring or something. No, that's actually an internal combustion event. There's a piston that we fill with fuel and light off and launch the robot. The sensing problem here is the trick was that robot needs to land reliably. There's a whole bunch of really creative mechanical engineering in the design of the wheels and things. But we actually had to have a flight control system on the robot so that it could control its orientation and land on the wheels in order to let the wheels work and absorb the landing shock. And so there's an inertial measurement unit in the robot, and there's a relatively simple control system built around that stabilizes the robot in flight. The bottom two videos are, two of our quadruped robots. This was a robot we called Wildcat. This is a machine that could actually run at about 20 miles an hour across a parking lot. Not difficult terrain, not laboratory floor terrain. And it was fairly maneuverable, fairly capable. This machine is blind, right? The only sensors it has are an inertial package inside of the robot, and then it has proprioceptive sensors in all of its joints. So it's measuring positions and forces or surrogates for forces in all of the joints. And that's what allows us to run really quickly. And then the last video you see, and this is a video we don't show that often, this is the early prototype of the robot that we now sell as Spot. So this is what we internally call Spot version 2. The distinction here, this is the first time we built an all-electric quadruped. Again, the sensing here is relatively simplistic, and yet it has really good mobility capability. And that comes from this idea of building these low-level behaviors and capabilities in a very reliable way and building upon those to get to the higher-level capabilities. So, I'm going to talk about how do we use sensors in a smart way. We can put a lot of sensing on these robots today thanks to advances in all these different industries and the availability of a lot of different technologies that I certainly didn't have access to even 10, 15 years ago. So Locomotion builds upon this idea of minimal sensing, right? We have locomotion control technologies that work very well when none of the sensors on the robot work. It blindly takes steps. When the proprioceptive sensors are working right and the robot can feel the ground, it walks much more effectively, much better. When some of the exteroceptive, the cameras on the robot start to work, then all of a sudden the robot can actually plan its footsteps and be very intentional about how it gets through terrain. As we transition to doing manipulation, the burden on the sensing becomes much higher, right? Manipulation, reaching and touching the world requires much more delicate and precise interaction with that environment, and thus it requires more sensing. We're trying to do the exact same thing that we did with Locomotion. We're trying to use these relatively simplistic, that's probably the wrong way to describe them. They're relatively complex, but the idea is they're not very dependent on external data, low-level behaviors, and build on those to produce more complex behavior. Matt Mason, who's going to speak after me, wrote a lovely 2-page paper back in 1993 called Kicking the Sensing Habit. And I think that the thing that's sometimes misquoted about that is people say, oh, it's about not using sensors. And I think the paper is really about using all the information that's available from the sensors and from the actuators or your models of your actuators in the environment in an effective way. And that's what we're really trying to do with a lot of our manipulation work. Why do you want an arm on a robot? Why do you want that robot to manipulate the world? You want it so the robot can actually go everywhere. And one of the huge obstacles for a robot are doors. So one of the base capabilities that we're delivering with our robots these days is door opening as a built-in behavior. And I'll let you just watch the video here for a second, and then second time through the video, I'll narrate what's actually going on so you get a good sense of what's happening. So at its core, this is an autonomous behavior. There's a little bit of human input and supervision at the very beginning. So right now when the robot's looking up, the operator is saying, the door handle is about there, and this is a door that opens towards you on the right side. Once the robot knows that, it reaches out with the arm. The arm has a set of sensors in the end effector. In particular, it's got a depth camera. And it uses that depth camera to actually find the door handle. Now, it's not using a very precise model for the door handle. It's basically looking for a blob of points that are protruding above a plane. Once it sees that, it does a servoed motion, a visually servoed or a sensor servoed motion to actually grasp the doorknob. And once it grasps the doorknob, it transitions into a set of impedance or force-controlled behaviors that are actually what allow it to effectively turn the knob, open the door, will actually, if we don't tell us that the door opens towards you, we'll try pushing on it and pulling on it and decide which way it actually moves. We don't have a precise estimate for where the hinge is, right? So it's not highly model-based, but rather the machine feels as it starts to pull on the door where the hinge is, and as a result, it knows where to put its foot to block the door and hold it open. So this is that idea of there's a whole bunch of information available to the machine that's not coming from what we would traditionally think of as sensors that allow it to be effective at doing this kind of behavior. Well, if you're going to do mobile manipulation, you better coordinate all of this stuff. So, right, we really need to coordinate body and arm motion. You see a particular example of that in the door opening case. We do need sensors to help us to adapt to unexpected events in the environment. We're relying primarily on imaging sensors and depth sensors, whether those are image-based depth sensors, time-of-flight depth sensors. We'll use whatever fits in the packaging we have available. And then we build relatively graded APIs on top of that. So if you want to control kinematics of the arm, you can do that. If you want to do high-level grasping commands, we'll allow you to do that. We'll let you program impedance. The door opening behavior I showed you is something that you can actually build on top of the robot as we sell it, up to the little bit where we put the foot in front of the door. That's the one thing we don't expose externally. And so this is just a video that gives you a little bit of a summary of what we can do with robots. Yeah, we can play jump ropes. Those two robots on the end are coordinating, right? They're doing things in a coordinated way to swing the rope. We can go out and pick the trash up. This is an almost essentially autonomous behavior, again, using a relatively simplistic high-level vision tools that are looking through the robot's cameras to find the objects. We can use our impedance interface to put the robot's arm into a mode where it can drag heavy objects, and it coordinates the way the body leans, right, the way that the robot locomotes in order to support that relatively high load. We can go do chalk drawings on the parking lot. That's actually a little bit trickier. You need the right kind of impedance control to actually effectively drag the chalk across the rough parking lot and not get stuck in the cracks and do things like that. The person who was working on that had a very strong computer science robotics background, and he said, "This will never work." And I said, "Oh yeah, well, we just got to turn this term on in the controller." And sure enough, a week later, it all worked really well. I just want to close with really one video here. This is where one of the things we're working on right now. This is what you would call a constrained manipulation task, right? So the robot's touching the world and pulling on something that exerts constraints on it, right? What you see is you see coordination between the robot's body and the arm. The thing to watch is actually to watch the hand. The hand, while it's moving, very smoothly, pulls the drawer open. There's a user operating this robot there controlling one thing, which is velocity at which the drawer opens in task space. And that's it. All the rest of this happens as a result of this sort of relatively low-level coordination in the robot and using primarily force sensors here to make things happen correctly. You can also do the same thing on more difficult tasks. The oven door has springs and it's relatively heavy, so the robot actually has to tug on it a little bit harder to get it to open. And the robot has to step out of the way so it doesn't bash itself in the head with the oven door, right? That's one of the things you want if you're eventually going to have these robots in your home environment. So that gives you a sense of the kind of things we're trying to do and how we're putting those together with relatively minimalistic sensing and trying to build up towards a capability that really leads us to effective autonomous mobile manipulation. And I'll stop there.
Thank you very much. It looks like we'll have soon robots that will not only wash the dishes, but also take them and put them in the drawer.
Hopefully make the cookies for you as well.
Very good. Alfred, I'm sure we have some questions in the room. Go ahead, please. Yes?
I love the door opening thing. I have not seen that. love the drawer opening thing. I hadn't seen that before, and immediately I'm trying to think of, I need help. I have these drawers, and they're all full, and so you pull it open, but it doesn't come open, and then you got to like reach in there and push things around, or you try shaking it for a while, and then I have other drawers that you pull it open, and it comes too far and falls out, and so I'm wondering if you guys are working on all of those problems.
Yeah, we're definitely not jiggling the door. We are trying to make sure we don't pull it out too far.
Very good. One more question. Yes, please.
I have a question about the teleoperation. Are you using the data that you collect from the real world to increase the level of autonomy of the robots, and what challenges are you seeing there?
Yeah, the one place where we're doing that relatively aggressively is with the door opening task, because we are selling the robots as autonomous data collection devices for industrial users, right, towards what Gunther was talking about earlier. It's really hard to get the data in older factories. Nobody's going to wire them. Nobody's going to put all the sensors in. People are interested in using the robots to walk through those facilities and collect data. Well, those facilities all have doors. They want to autonomously have the robot open the doors, right? They don't actually want to go actuate and put sensors in and IoT devices to automate door opening. So they want the robot to actually open the door. There is a huge variety of doors out there. So one of the places we do this pretty aggressively is in that domain. And so we have, machine learning algorithms that are improving our ability to recognize doors, automatically find the handle and the hinges, and basically take the place of what we ask the operator to do whenever we're doing that. We've also been doing a bunch of studies related to sort of situational awareness issues around teleoperating these robots. We have some customers in the sort of first responder space, public safety space, that are trying to use the robot in place of other robots they have traditionally used. And we had not actually designed it with that in mind. So there's a bunch of learning for us there as well, but that's more engineers learning rather than machines learning. I don't know. I guess that's about the best I can do in terms of answering that.
Thank you very much, Alfred.
Thank you.
Thank you for introducing us to the latest solutions of mobility and manipulation in robots. Now we go a step further into robotics of warehouse automation from robotics research at the Berkshire Grey. Professor Matthew Mason is chief scientist at Berkshire Grey. He has his degrees, including a PhD from MIT, particularly the AI lab, at Carnegie Mellon University. He served as the chair of the robotics PhD program, and he was also director of the CMU Robotics Institute. He has won a lot of prizes in the field of robotics and automation. I can't go through all of them, but it's you're very respectful when you read it. A good list. Now we are curious to hear how you transform warehouse and distribution centers. And of course, order fulfillment, parcel solutions, store replenishment in related operations in warehouses are interesting. Since I have been in charge of a business that we call Siemens Thematic that does parcel centers and letter sorting and things like this, I'll be looking very curiously at your presentation.
Oh, I'm going to have to
Thank you very much for the kind introduction. Thanks to everybody for coming to listen. And see if that does that. I won't push that button. Black, that sounds dangerous. So the plan for this talk is to talk about a transition in my life. So most of the time I worked at Carnegie Mellon, and my goal was to publish papers and the occasional book. And sometimes in order to do that, you had to do some robotics, okay? And I focused almost entirely on robotic manipulation ever since 1976. And then a sudden transition happened, and now my goal is to pick toothpaste out of a bin. And so, you know, maybe there's something that can be learned. You know, you can view this as setting the baseline and then view that as the experiment, and we can see whether I learned anything from the transition. And I'll talk about that a little bit at the end, lessons learned. But you might ask, you know, what happened? When did this event happen and why? And I can tell you exactly when it happened. It's on still on my calendar. On May 6, 2014, I got a visit from Tom Wagner, who is the founder and CEO of Berkshire Grey. And at 10 a.m. on that day, I thought that there would be no immediate applications of autonomous robotic manipulation beyond factory automation. And you know, you can go down a list of different ideas, and I didn't believe in any of them. And except for the Roomba. I was wrong about the Roomba. But some people don't know that the Roomba is manipulation, right? It's picking up little particles of dirt. So that's an exception. And then 2 hours later, I was convinced. So in this metaphor, this is Tom Wagner, and this is me, and he hooked me. I was totally hooked, and I'm still hooked, okay? He had a vision, and now I'm hooked on that vision, and I'll try and convey a little bit of that to you. Here's the actual timeline for it. So I started in grad school doing manipulation in 1976, went to Carnegie Mellon in 82, so that's like 40, is it really 18, 22, 40 years ago. And all that time, manipulation. And let's see, here I am at Berkshire Grey, except actually I didn't go to Berkshire Grey until 2014. So here's the event where he hooked me. So let's back up a little bit in time. What was Tom Wagner doing that led up to this? Well, he was the CTO at iRobot. And in 2012, he left and he went on what I'll call a vision quest. He spent a year. It's not like some startups where you take a technology, an idea that you love, and you take it into industry. He did it the other way. He had a whiteboard, and he had a list of 45 ideas that might work, and it was all over the spectrum. You know, there was agriculture, there was manufacturing, there are many different ideas. And one of them was, you know, we call it warehouse automation. It's a little broader than that. It's, you know, distribution centers and shipping centers, and also like the receiving end of a factory and the shipping end of a factory. But we just call it all warehouse automation. And, you know, why did I need to be convinced? I thought that it was a solved problem, and I was naive, but still a lot of people still think that, and it's definitely not. I'm going to show you a lot of robots doing great things in warehouses, but you know, for every one of those, I mean, the part that's been addressed is still a thin slice. And what Dr. Cagle was saying about human capability versus robot capabilities, I agree with 100%. It'll be quite a long time before before warehouses are really fully automated. So I actually think this is a great area for research. If I was to make the transition the other way, I would be focusing on warehouse automation, because I think it's a great source of ideas. And if you're a grad student thinking about, you know, what can you do that's different and new, I think it's a great application area to drive some interesting work. But anyway, let's see. So yeah, BG was founded. There's me getting hooked. And then 7 years later, Berkshire Grey went public. We're listed on NASDAQ, and we're actually the first company in the United States to go public, the first robotics company to go public since iRobot, like 16 years ago. So I was surprised by that. You would think that was a more common event, but it's pretty rare. So I'm going to talk a little bit about the technology, and I'm going to show you a few systems working. Where the technology started, the thing that I was focused on is each picking. And there's a little bit of jargon. Okay, if you're I mean, there's a hierarchy, a sort of recursive packaging hierarchy in logistics. You know, you have like containers or trucks. A truck's just a big box on wheels. And then inside of that, you have pallets. And then inside of that, you have cases. And then inside of that, you have boxes, right? So there's this recursive packaging hierarchy. And then at some point, you get down to eaches. And you could go even further. I guess an each is identified as the thing that you would see like on a shelf in a retail store or in a grocery store. And there are a lot of systems that can pick pallets. You know, we call them forklifts, and systems that can pick cases that are these big suction arrays. But picking eaches is special because there's such an enormous variety of things. Okay, just think of all the things that you see when you walk into a big retail store. It's an amazing variety, and you need a system that can pick all of them, and that's where we started. So I'm going to show you, this is just a montage of several of our picking things, and we'll come back and look at some of the systems you're seeing here in a little more detail. But so, you know, there's our gripper, and this is an early version of it. There have been some refinements since then. The point is that it's picking a lot of different things. So here are some kind of loose bags of apparel. Here are some rather heavy bottles. Bags are interesting for vacuum because they have wrinkles, and the wrinkles let air in, which is bad. You can buy special bag grippers, but we don't want special grippers, right? We want general grippers. So now one thing that's key here is vision. And the vision is figuring out where to grasp things, and it's also very quick because the things move. So right away, it's figured out the next place to grasp. But this is the thing that I'm most proud of because it grasped that thing right across a seam. Okay, there's no way that you can get a seal across that seam. And most vacuum systems struggle with that. It can even pick these porous things, these bath sponges, or a baseball cap. Being in the Pittsburgh office, I find this video really annoying. I don't know if they did it deliberately to have me pitching a Boston baseball cap, but here it is working in the back of a grocery store. So as far as I know, I've never seen another system that can pick the variety of items that our systems can pick. And it doesn't just pick, it also packs. In this case, it's doing e-commerce order fulfillment. That box is going to be closed, and that plastic you see there shrinks, and that box gets shipped directly to a consumer. So that is an e-commerce fulfillment system. So let's look at a couple of things in more detail. One thing that Berkshire Grey, one thing that's part of Tom Wagner's vision was he did not want to just sell a component. He didn't want to just sell people a robot. We sell whole systems. And so that means the upstream conveyance, the downstream conveyance, all kinds of surrounding stuff. Because if you just sell a robot, you don't get the full value that you get if you can optimize the entire system. Because the operating characteristics of a robot are different than a human. So this is a sortation system. This is installed in some FedEx facilities. So this is a shipping center. Again, you see a large variety of items. There's an awful lot of bags, but there's also boxes. There's flat envelopes, round things, cylindrical things. These annoying, very annoying triangular cylinder things that are a challenge. And so a human tosses the bag of this stuff into the conveyors, and then it drops it through this vertical scan tunnel. So this vertical scan tunnel is also a Berkshire Grey thing. It can pick up the barcode, whatever orientation. There's lots of lights and lots of cameras in there. And I don't know exactly why, but it also does a really good job of picking up barcodes, even on wrinkled plastic things, which can be a challenge because the wrinkles can obscure the barcodes. And so now, as it comes out of that, it's called the hyperscanner. As it comes out of the hyperscanner, it's singulated, it's identified, and now it's going to kick it into one of these linear shuttles. And so this is a different configuration of conveyance than you usually see. This linear reciprocal thing, somehow our guys came up with that as a better fit to the characteristics of the robot. It's also very modular, scalable. It doesn't take up a lot, as big a footprint as some competing systems. And we're going to see another application of that linear shuttle thing in a moment. So that's our stuff working in a shipping center at FedEx. That's the only customer I'm going to tell you the name of. There's, I don't know, there's contracts and stuff. Some of the names are not really secret. You can find it in the, you can find Berkshire Grey mentioned in the quarterly earnings reports of other retailers, but I'm not allowed to say the names. You'll have to do some research. So e-commerce. This is a system called a put wall, which is something that manual picking uses. Humans use this. This is an auto bagging system, so now it's feeding items and dropping them into this machine that automatically closes the bag, and so that's this is, you saw a glimpse of this before. This is the grocery packing system. Here, pose in hand is an issue. There's a camera, an intermediate camera. It pauses briefly to get a snapshot so it knows exactly where that object is relative to the gripper, because you need some precision when you're placing it into the bag. That might be all of that. Okay, store replenishment. Turns out, initially you think, well, it's all about e-commerce. It's all about e-commerce. E-commerce is growing at a dramatic rate, and yet it still has a long, long way to go. The vast majority of retail is still happening through brick and mortar stores, so we got a long way to go on this. Well, why not help the brick and mortar stores with the systems as well? So store replenishment. It turns out if you go to a big retailer, they have regional distribution centers, and each distribution center serves several of their local retail stores, and those retail stores order the things they need to replenish their shelves, okay? And this is a system that uses 4 of those linear sort wings in parallel to replenish stores. So what you see here in the gray bins, this is inventory that's coming in from an automated storage and retrieval system. It's coming to our picking robot, and the picking robot drops it into another one of those linear shuttle things. And it's dropping it now not into a bag, but into a box. Those boxes have a plastic tray and a plastic cap because an empty cardboard box doesn't convey very well on ordinary conveyors. And the plastic cap holds the flaps down and lets us fill the box more efficiently. So each of those 4 systems is sorting to several boxes. The boxes are getting, it's getting fed automatically. So unlike the FedEx system, am I running out of time already? Okay. Anyway, the induction and the extraction here are happening automatically. In that case, I'm moving on. This is another store replenishment system. Now, this is obviously a different philosophy. So instead of the linear sort wings, now we've got a 2-dimensional array for distributing stuff. We've got a fleet of mobile robots. We've got a high-density buffer in the middle. What's not shown is there can be an automated storage and retrieval system. To think about this system, what you want to think about is it's like memory cache, okay? You bring out a lot of inventory out onto the floor, and that stuff can be handled in a much more agile way by this fleet of mobile robots, okay? So the shelves that are spread on the floor are like a low density, but very high-speed, agile system. And you can have people doing the picking if you're doing order fulfillment with this system. You can have robots doing the picking. You can have a mix of them. The induction and the extraction are automated. The beautiful thing about this is that it does what we call aisle-ready replenishment. So when the stuff gets on the cart, when the stuff gets in the truck, it's organized in accordance with the aisles in the store that it's going to. So the robot system knows what the right order is so that when the stuff comes off the truck, it comes off in the right order. You just take this cart right to the end of the aisle and boom, 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 and it's much more efficient. So like an hour or two rather than a day to unload a truck. Yeah, what's the time situation? Am I out?
We're over it.
I'm over, okay. I don't know where I blew it, but somewhere I went over. There's that. Robotics research tends to be here. Warehouse reality tends to be there. Lessons learned, it's hard. Warehouse manipulation is really hard. You don't appreciate it because you're a human being. Thank you very much.
Wonderful. Wonderful. Thank you so much. It was a great presentation, and I'm sure there are many excited people that would like to ask questions. Any questions? Please.
I have one question. If you look at your examples, there is not a humanoid robot in the. There is no humanoid packing the stuff in the boxes, but you have suction manipulators and things like this. So how important is it to think outside of the box? Do we really need to imitate the human operation, or you seem like to go other ways just to simplify the process?
Well, one way to think about this is to think about the, if a human is a walking manipulator. Now, when a human is shopping, right, they're carrying the manipulator, they're carrying everything down the shelf. An awful lot of what human pickers are doing is transporting themselves. Some of the time they're transporting goods, sometimes they're just transporting their manipulators and their feet, right? It turns out it can be much more efficient, and this all varies depending on the system, and I don't know that much about the statistics of it, but it can be much more efficient to arrange for the stuff to come to the human rather than sending the human to the stuff. Okay, so that's why people talk about goods to human. We also talk about goods to robot. Now, there's a variety of things here, but as far as I've seen, I haven't seen one yet where the right idea is to have a mobile manipulator moving around. I'm sure they're out there, but I haven't run into them yet.
Now, coming from that sort of business, a question regarding investment. The way how we do parcel centers and letter centers and baggage handling centers, there's a lot of infrastructure, football fields full of mechanical stuff, a lot of investment. When I see your last solution with the mobile robots carrying things around through rather less infrastructure, would it be much less investment?
Is there less investment in infrastructure? Yeah, that's a good question. I don't know.
From a business point of view, that might be very interesting for customers.
I do know one thing, which is that customers with existing infrastructure are greatly concerned about how we fit in with them, and so because of the modularity and the scalability of it, we can install systems one chunk at a time as they remove their previous system, and that's what happened with that first store replenishment system that we saw. Is the infrastructure overall less expensive? I don't know the answer to that. I'll pass that one along.
Yeah. Thank you very much. Wonderful. Now we go to another element which I think many in the industry also will be concerned about, trustworthy AI and trustworthy machine. We'll hear Dr. Christoph Palo. He is the project manager for the Digital Trust project at Bosch and leading the Bosch Center of Artificial Intelligence. He was a member of the high-level group of AI in the European Commission, which was very much thinking about the rules for trustworthy AI. And he also worked at Deutsche Telekom Laboratories in Berlin in the area of AI, cybersecurity, industrial 4.0 and IoT. He has a degree in computer science and computational linguistics and artificial intelligence. His PhD is from the University of Osnabrück. Now, Christoph, welcome. Here you are, wonderful. Thank you very much for coming. We are very curious how we handle the trustworthy problem of our machines then.
Good afternoon. So I think this talk of me will be rather surprising because frankly it stretches the semantics of perception a little bit, talking now about ethics and trust. But there is no clear censor for ethics and for trust, and so might be that there is some fit anyway. And although I'm from Bosch, my talk today is not technical. This might be disappointing for you. However, I invite you to follow on a path less traveled by computer scientists. However, important if we want to bring AI products and sophisticated AI products in the European market. And this because trust will be required there. And this is what my talk will be about in the next 15 minutes. Okay. So, actually, when we speak about AI today, I think we are just discovering and speaking about the tip of the iceberg. Although it's tremendous what we can do with AI, still in my regard, it's more sophisticated and glorified pattern recognition. So there is a lot more of AI, of intelligence, what we can use. But even with that tip of the iceberg, we are addressing both fantastic applications for industry. You saw a variety of that today and downstairs as well. However, frankly, some people are very concerned that it might lead to a complete fundamental change in our perception of reality, how we interact then with each other, and you know this item of how we collect information, this echo chambers, deep fakes, and so people are concerned what will be the future if we rely too much on AI, if we have AI unregulated, and this is why legislation and standardization in Europe kicks in here tremendously. And as Mr. Kegel rightly said earlier, working in standardization is no fun. And adding legislation for that doesn't make it better. However, it's important and to bring the products to the market. Speaking of trust, trust needs foundations. And next time you are visiting the Pope in Rome, please see this picture. It's in the Vatican, and it's a picture which combines the basics of philosophy and different approaches which were essential for Europe. We see here Plato and Aristotle. I won't get into details because this is rather philosophical. However, if we seek for foundations of trust, you have to stick either for universal principles like Plato or more empirical based like Aristotle, and this was the way more or less Europe decided to follow. And thus our notion of trust as assured reliance on the character, ability, strength of someone has to do with experience gained over time. I'll give you an example for that. I'm sure you have trust in your parents, but probably you don't trust your parents to fly a plane. So for trust, we need competence, entitlement, positive mindset, and a certain transparency so that we understand the underlying logic of that. And if that all is given, we have then a configuration where we trust even to board a plane and use it accordingly. However, in the digital world, it's rather different. First of all, we do not have this stable environment, this stable shared environment where everybody might refer to implicitly. A lot of implicit information is in our everyday setting so that we share more or less the same reality, and our experiences are grounded and based on that. In the digital world, it's completely different. What we call digital world is it's a bunch of communication protocols, telecommunication systems, and so on. Constantly under change, constant flux. We do not have this kind of stability to get a reliable experience on that. And even the systems we are using in our products, many people don't even understand what really the core of the system is, which has to be trusted. So this trusted computing base. And why is that? It's because of the increasing complexity we are facing in the digital world. So I sort of nicked this nice picture from a publication of the US Air Force. It's already, it's from 2015 or so, but it looks rather actual. But we see all this complexity rising, and they identified then as how to cope, the ability to cope with complexity is the PhDs in computer science or so here in the US. So this is more or less stagnating. For Germany, it would be even sobering. So we have left that curve out here. And you see Chinese PhDs are slightly better. But in general, the message of this is that our ability to cope with the complexity is at least not rising. And AI, although it's fascinating, it's not precisely a democratic technology because it needs a lot of resources for being successful in AI. When we started with computation, so the promise of the desktop computer, 1984, this famous advert of Apple, was unleashing the power of computation at your own fingertips, in contrast to the mainframe systems. Today, since it's all cloud-based and incredibly expensive, it changed. So take AlphaGo, fantastic from AI perspective, what people achieved here, however, quite expensive. The training of 40 days cost roughly 20 million and consumed the power of 30-something households in Germany, the yearly energy consumption. So it's not cheap and even not affordable by most universities here. So AI and making sophisticated use of AI is concentration of power, and the next steps of AI in foundation models doesn't make it better and doesn't make it more transparent. So this trust issue I already mentioned is, at the end of the day, justified. As the trust in IoT is broken, we know it for a long time. I have some credentials here, lousy IoT security. This is to say it polite. But putting now AI on something we don't trust anyway, you could ask, is that the right decision? Is that the right strategy? And we have here the testimonial of Werner von Braun, someone who knows about power, how power can perhaps corrupt or influence people, and how difficult it is to keep that power in check. And keeping that power in check is exactly what we have to do here to use then the light sides, the bright sides, the promising sides of AI in a responsible way. And we have to formalize digital trust. Digital trust is, for us as industry, it's sort of the digital equivalence of our traditional promise of superior quality. And so it's what we are now facing by legislation and standardization, that even law asks for trustworthy AI. Just think about it. It's very untypical that a law states we want to have a trustworthy technology, because trustworthy is not a legal term. But we have to understand that this is a sort of very formal way to express the expectations of the customers and of the society, and we as industry should listen to our customers, of course. And we should ask our customers, what degree of trust do you want in your product? What kind of trust is that you require? And for that, we founded a sort of consortia, worked with other companies like Siemens and with standardization bodies and VDE to work on such a trust seal, a trust label, which makes it explicit what we mean by trust, and so that the people, the consumers, can choose what kind of trust they would like to have in AI products. And offering them the opportunity to choose between different flavors of trust is important, because trust is a personal thing. Trust lies to a certain degree in the eye of the beholder. Trust is value-oriented. And so making values measurable is difficult, right? And it's not a mathematical science. However, you can do with some easy approaches or easy explainable approaches, which at the end of the day make sense and provide a certain measurement. Starting with the values, the core values you have, like transparency, fairness also. Identifying criteria for that, when that value is met, showing indicators and observables, because a value and the implementation of a value has to be observable in some way. And this is basically what we did with checklists, so that you can then label your products, your AI products, in terms of what level of integrity, entitlement, competence and mindset, the 4 dimensions I gave you earlier. We mapped that on this privacy, transparency, reliability, accountability, and fairness, which happen to be core dimensions of what AI Act, the European AI Act, defines as trustworthy AI. And so giving the producers of AI some guidance and some checklists at hand to point out what levels of trust they can offer, so that the consumer then can pick the level of trust which is desired. I think this might be a right step, or we think that might be the right step in the direction that industry is able to produce trustworthy AI products and create that trust in the market and this acceptance of AI in the market, which helps us to bring even more sophisticated AI solutions to the market. And then we can really unleash the power of AI for everyday products, for products which do not only support decisions of humans, but to a certain degree do their decisions of their own, so that we have the trust that we can delegate certain decisions to AI systems. Investing in that makes a lot of sense, because for businesses and industry, I think it's still valid what Robert Bosch earlier said. I would rather lose money than trust. So inventing in trust makes a lot of sense. And since we have no perception of trust, no sensors of trust, we need approaches to approximate that. So this talk was quite different from the other talks of this afternoon session, but I hope you take something with you anyway. Thanks for your kind attention.
Wonderful, Christoph. Thank you very much for this introduction to the trustworthiness of our robots. There may be questions concerning this topic. Any question that you... Go ahead.
In what part of the scale do you put your own products that you're developing in this area? in AI?
We as Bosch always try to be leading in every aspect. So all A rankings, yeah, on all 5 categories. That's at least the aspiration level.
Another question, yes?
So this requires an education of the consumers as well, right? To be able to interpret the level of the this labeling. This seems to be quite difficult, right? Because even for the experts, determining the level of trust in an AI system is difficult. And now with these labels, we need the consumers to be able to interpret them as well. So is there an educational aspect of it for the general public, or?
There's a communication aspect in that as well. Yeah, I hesitate to say it's education, it's more communication, but we have the situation that legislation says industry, you don't understand what your customer really wants. They want trustworthy products, and we define what trustworthiness means. There might be a gap in the understanding of politicians and consumers. However, we are forced to close the gap. Yeah, to say politics, okay, we understood. Look, this is how we approach that, and we have then to tell our customers. So what we understand of what you want. Yeah, trust might be related to fairness. Yeah, it might be to transparency, accountability, human in the loop, or whatever. And so those are the categories you can choose from. And with your choosing, you will influence the evolution chain of future AI products. If you pick more regarding transparency, then the result will be that we have more products which put more emphasis on explaining what kind of AI is in there and how it works. And if it's something else, then the evolution goes in another direction. But we have no chance here. Yeah? We have to obey legislation, of course.
A question on my mind regarding this is certification institutions. I'm sure in the European Commission task force you were discussing issues, how do we certify products? If you take your picture, the plane was certified by FAA, the Federal Aviation Authority. The pilots had a certified education. The engineers that were building the plane had certified education by some universities. So we all rely on these certifications in the real world. How do we do this in the AI world?
Likewise. So it's the kind of certifications we have is related to the risk. And if you have some issues where you could lose your life or your health, like aviation is a good example for that, then you need a third-party certification done by third-party authorities which have the competence of doing that. And what we are doing now, or what politicians are doing now in AI, is redefining what risks are. It's not just the risk of life and death, but risk of civil rights being questioned or being diminished by AI applications. So this as well is now a severe risk. And for such an AI system, you will need later then a third-party certification. There are, of course, benign applications from AI which have the character of a decision support system. For that, you need an own declaration, but not an external certification. So it will follow these established lines.
Yeah. Thank you very much. So we're looking forward to the world of certification institutions that are coming towards us when we use AI. Thank you, and an applause again for Christoph, please. Now, we are coming very close to the application of systems also in industry. And I find we have gone through a rather different spectrum of presentations as compared to what we had earlier. We will continue this in the next session with a rather different approach again, namely learning, understanding, and interaction. And I would like you to look forward to Professor Wolfram Burgard, Melanie Wise, Professor Jens Koba from the University of Delft, Professor Giorgio Meta from the Italian Institute of Technology. So please get your coffee now. Professor Stefan Leutnegger will be your host and moderator in the next session. Don't miss it, please. All the best and have fun in this conference.